right, these are the notes for section 10.2 on arithmetic sequences. The 4 things we want to accomplish in this section are we want to find the common difference for an arithmetic sequence. We want to write the terms of an arithmetic sequence. We want to use the formula for the general terms of an arithmetic sequence. And we want to use the formula for the sum of the first n terms of an arithmetic sequence. Okay, so let's start with the basic definition of what an arithmetic sequence is. So an arithmetic sequence is a sequence in which each term after the first differs by the preceding term by a constant amount. So the difference between that consecutive terms is called the common difference of the sequence. All right, so let me give you some examples of some arithmetic sequences. So let's do 7, 10, 13, 16, and so on. So this would be considered an arithmetic sequence because it has this pattern when we go from one term to the next term, which is a plus 3, plus 3, plus 3. And that plus 3 is called the common difference. Now, it's called the common difference because if you do 10 minus 7, you get 3. And if you do 13 minus 10, you get 3. And if you do 16 minus 13, you get 3. We use the letter D to represent the common difference of an arithmetic sequence. And in this case, that would be 3. Okay, so let's take a look at, let's see something a little bit different. So let's do 5 plus 2x. Our next term is going to be 3 plus x. Our next term is going to be 1, just 1. Our next term is going to be negative 1 minus x, and so on. All right, so what's happening on this particular sequence is when we go from one term to the next, we'll see if I did this right, I'm doing minus 2 minus x. So 5 minus 2 is 3, 2x minus x is x. So then to go from 3 plus x to 1, I subtracted 2 and I subtracted x. And then to go from 1 to negative 1 minus x, I subtracted 2 and subtracted x. So for this one, our common difference would be negative 2 minus x. So arithmetic sequences can be numerical, but they can also be algebraic in nature, like the second one I did here. All right. So for our first example, we're going to write the terms of an arithmetic sequence. So we're going to write the first 6 terms of an arithmetic sequence, which a sub 1 is 100. So that means our first term is 100. And then what we have here is a recursive formula that's telling me to get to a term in the sequence, I take the previous term and subtract 30. Okay, so let me just write it out if you were going to be writing out the work. So if I want to find the second term in the sequence, what this tells me to do is do a with a subscript of 2 minus 1 minus 30, which would be a sub 1 minus 30. A sub 1 is 100, so 100 minus 30, which means we're going to get 70. So 100 and then 70. Okay, now after I kind of understand what this is saying, what I know is that the common difference here is subtract 30 each time. So now my next term is going to be 40. My next term is going to be 10. My next term is going to be negative 20. How many am I here? 1, 2, 3, 4, 5. So one more. Negative 50 are the first 6 terms. Now that would keep going, but they've only asked me for the first 6 terms, so I can stop there. So this is the sequence they're asking about. All right, one of the big parts about arithmetic sequences is being able to understand their formulas, kind of understand where they come from, make connections between the graphs and things that are arithmetic. So this slide is going to take us a little bit of while to kind of develop your understanding. So we're going to consider the sequence 7, 4, 1, negative 2, negative 5, 8. Now, the first thing I'm going to do when I look at the sequence is start to think about why it's arithmetic. So if to go from 7 to 4, I subtract 3. 4 to 1, I subtract 3, and so on, and that pattern continues to hold. So that's how I know this is arithmetic, plus they told me up here, and it has a common difference of negative 3. Now I'm going to graph this sequence. Now remember, when we graph a sequence, the x-axis for sequences is n, or the term number, and the y-axis is the a sub n, or the term value. So in this one, the first term is 7, which gives me that point right there. The second term is 4, which would give me that point right there. The third term is 1. The fourth term is -2. The fifth term is -5. The sixth term ended up being -8. And we can see when we start to graph arithmetic sequences that they form a pattern. Arithmetic sequences always lead to a linear pattern. Now that's because of the common difference. So the common difference is telling us how many we're subtracting from the term. So we're going to go down 3. That's why we're subtracting 3. To get to the second term, we go over 1. And then to get to the next one, we go down 3, we subtract 3 from the term value, and then we go over 1. So in terms of a graph, the common difference is going to be equal to the slope. So slope and common difference are going to be the same thing. Down 3 over 1, down 3 over 1, and so on and so on. So that's true of all arithmetic sequences, is that the common difference is equal to the slope. Now there's a couple of ways we can write formulas for arithmetic sequences. And we can do this in slope-intercept form, or we can do this in point-slope form. So in slope-intercept form, now remember, slope-intercept form is y equals mx plus b. Now we just have to kind of remember that with sequences, we don't use y and x as our letters. So when we do sequences, y is a sub n. So a sub n, I'm just going to draw an arrow here, what this is going to become, equals m. And for x's, we don't use x, we use n to be the term number plus b. Oh, and b, let's actually change that. Actually, let's change the m. Sorry about that. Because m for sequences is d. And then b would be the y-intercept. Now the y-intercept would be, in this case, up here. Went a little bit off the graph. But that's going to correspond to the 0th term of the sequence. Now, I assumed on this one that I started counting at the first term, and that's why I graphed the way I did. But if we went back to the term 0, that would go backwards, and that would be my y-intercept. So for this question, what that would look like would be a sub n equals the common difference, which is -3n, plus a sub 0, which would be 10. 10 is what I would get if I went backwards in the pattern, one more term. I would have started my 0th term, or the term that would be graphed on the y-axis, at 10. And I'd subtract 3 and go to 7, and so on and so on. So that's one formula that works. Now that formula is super flexible when we start to think about point-slope form of a line, which is actually my preferred way of doing these kinds of problems. Because in point-slope form, I don't have to have this 0th term here. In point-slope form, I can use any point on the whole entire graph. Now, as just a quick reminder, point-slope form looks like this. Y minus y sub 1 equals m times x minus x sub 1, where the x sub 1, y sub 1 coordinates come from any point on that whole entire graph. Okay, so I'm going to do this time with, let me just use the first term. That's a pretty common one to use. So now remember, instead of y, I don't use y's for this. I use a sub n. And then I'm going to do minus y sub 1, which is the y coordinate, or the value of the first term. In this case, that's going to be 7. So that's coming from the point I have highlighted there in pink. For sequences, I don't use m, I use d, so common difference, -3. And then instead of x, I use n, and then minus, and then x sub 1 would be 1 in this case. That's the x coordinate of that point that I've highlighted in pink. Then usually for sequences, we want to get that a sub n isolated on the left side. So I'm going to add 7 here to both sides of this equation. And that's going to look like this, -3, n minus 1, plus 7. So if I was sort of, so that's the specific one for this question. If I was generalizing that, so like I did up here, this is the general formula for any sequence, any arithmetic sequence. If I was generalizing this one for any sequence, it would be it would be d, the common difference, times n minus, and then whatever term you're going to use. So I'll just use 1 plus a sub 1. Because the 1 here would correspond to the first term, the a sub 1 here would correspond to the first term's value. Okay, so that would be a formula we could use. Now that's super adjustable, because what if I wanted to use the second term instead? Then I could do n minus 2 plus a sub 2. Okay, and that would be using this point right here that I'm boxing right now. I could, because that's the second term, it has the x coordinate of 2, that's where the 2 is coming from. And then the y value of that would be that a sub 2 value, I would use a 4 there. So with specific numbers for this sequence, it would look like this, -3, n minus 2. the second term's value is 4. Now, all three ones that I have circled on this page are all the same then. If you simplify them, like distribute and combine like terms, you get the same thing either way. Now, another way that students can sometimes understand where the equation coming from is it's kind of just a different way of looking at the sequence. So we did this one very graphically. We talked about slope-intercept form and point-slope form, but sometimes students don't rely on graphs to understand the pattern for where the arithmetic sequence comes from. Okay, so I'm going to just show you and present this to you another way. I took a class in college when I was getting my second degree in computer science that had us do these patterns like this. Okay, so my first term is 7. And then to get to my second term, what I do is I do 7 minus 3. Now to get to my third term, starting at the first term, which is 7, I subtracted 3. That got me to my second term, and I subtracted 3 again, and that would get me to my third term. Okay, and then to get to my fourth term, I would start at 7, which is here. I'm going to subtract 3 again. That gets me to 4. If I subtract 3 again, that gets me to 1. And if I subtract 3 again, that would get me to negative 2. Now I can continue that one more time to get to my fifth term. I would do 7 minus 3 minus 3 minus 3, but then I would need to minus 3 again, subtract 3 again, and that will get me to my fifth term. Okay, and if we start to look at that, right, writing those minus 3s is going to get old, right? I don't want to do that if I have to get to my 100th term. So we're going to shorten that up by writing it as a multiplication expression. So in this first one, I took 7 minus 3 0 times. I didn't subtract 3 from it at all. To get the second term, I took 7 minus 3 one time. I subtracted 3 one time from 7 to get the second term. To get to the third term, I subtracted 3 from 7 2 times. And then to get to the fourth term, I subtracted 3 from 7 3 times. And then to get to the fifth term, I subtracted 3 from 7 4 times. And that pattern would continue. So what we want to do is we want to generalize that for a sub n. So to get to any term in the sequence, what I'm going to do is I'm going to start with 7, the first term, and I'm going to subtract from that, in this case, 3. And then what I want to look for here in parentheses is the relationship between the term that I was trying to find and how many times I subtracted 3. So when I was trying to find the third term, I subtracted 3 2 times. And when I was trying to find the fourth term, I tried to subtract 3 3 times. So the pattern here is that I'm subtracting 3 n minus 1 times to get to the nth term. Okay, and again, if I look back at this one that I have, let me highlight it in yellow here. Right here, that's the same formula. It's just that my plus 7 is out in the back on that one. And on this one, my plus 7 is out in the front. But some students understand it this way a little bit better. Okay, so to kind of summarize all of that, the nth term or the general term of an arithmetic sequence with first term a sub 1 and a common difference d, the most common explicit formula that we use to find that is a sub n equals our common difference or our slope, n minus 1 plus whatever the first term was. And that'll hold true for all of them. And remember, that's adjustable. If you don't want to use the first term here, you can change the number here. Okay, but that's the one we're going to use the most often when we're dealing with arithmetic sequences. So for our second example of this note, our last example for this note set, we want to find the ninth term of the arithmetic sequence whose first term is 6 and whose common difference is 5. Now I'm going to show you this with the formula, but I want to talk about something else too. So the first thing I'm going to do is I'm going to write a formula for the general term. So in this case, my common difference is 5, so I'm going to have negative 5. The first term is 6, so it's going to look like this, n minus 1, and then plus 6. Okay, so it's like saying if I'm going to find the ninth term, I'm going to subtract 5 from 6 8 times. So if I'm trying to find the ninth term, it's going to look like this, negative 5 times 9 minus 1 plus 6. So I started with 6 as my first term, and I subtracted 5 from that. Oops, I wrote 8 instead of 1 there. Sorry about that. I was thinking ahead to what that was going to be. I'm going to subtract 5 from 6 8 times to get the ninth term. So finishing just out the math here, it's going to be negative 5 times 8 plus 6, or negative 40 plus 6, which is negative 34 is my ninth term. Okay, but I always have students, like when they're taking the tests or the quizzes, that like get so hung up on the formulas. And yes, formulas are necessary and formulas are important. But I mean, if you just think this one through, if you started at 6, you want to find the ninth term, you can just start subtracting 5. You get 1, negative 4, negative 9. It doesn't take that many times before you get to that ninth term, just to like have it as a double check, or another way of doing this. So negative 14, negative 19, negative 24, negative 29, negative 34. So first, second, third, fourth, fifth, sixth, seventh, eighth, ninth term, negative 34. Now, at some point, that gets unreasonable. Like if I ask you, okay, find the 75th term. Like nobody's going to continue this list out till you get to the 75th term, because that's just annoying. Okay, so you have to have kind of a personal limit, and that's really what the formula is good for. All right, that's the end of these notes.